Hey guys, so today we're talking about light, and actually, there's a dual nature to light. Light can actually be thought of as either a wave, or light can be thought of as a particle of energy. Now, if we think of it as a wave, we call it electromagnetic radiation, and if we think of it as a particle of energy, we call it a photon. So, this is part two. We're going to focus on the wave nature of light in this video, and then part three will focus on the particle nature of light. All right, so part two, the wave nature of light. You can think of light as a wave, and if you do so, we call it electromagnetic radiation. Now, I'm going to show you a few examples of the ways in which waves behave, and then I'm going to show you that light behaves in that exact same manner to show you that it is, in fact, a wave. Okay, so first one here, we have a video that is generating waves, right? Now, over on the right is where the waves are being generated. There's sort of a wall there in the middle, and this wall has a tiny little hole in it, which allows the water to go through. The waves are actually going through that hole. Let me get it started here again. So the waves are generated there on the right, and then they go through that hole, and as you can see, what happens there is they bend. Right, now the size of the hole determines how much they're going to bend. So down here I have this picture. Get my mouse. Down here I have this picture here where if you have a bigger hole, it bends a little, but if you have a smaller hole, it bends even more. So the smaller the hole there, the more it's going to bend. This phenomena is known as diffraction. Okay, it's the bending of waves around an edge as it goes through like a small hole like this. Those waves will actually bend. Happens with water waves all the time. It even happens with sound waves. Okay, it also happens with light waves. This is actually what's happening with our spectroscope. So if we have a light source, that diffraction grating that's in your spectroscope, it's called diffraction for a reason because it's bending around the edge. That diffraction grating is actually basically just little slots that the light can go through, and there's parts that it can't go through. When it goes through those tiny little slots, the light is actually bent slightly, and when it bends, you actually get it to separate into its colors because the red will actually bend a bit more than, say, the violet or the blue. So white light, which is all of them, goes through these little slots. It bends it and kind of spreads them out so you can actually see the individual colors there. All right? Now, when this does happen, take my mouse over here, some of the light just goes straight right through and doesn't get bent. So we do actually are able to see the original light source when we're looking at it. Like if my eye was over here, I was looking at it, I would be able to see the original light source right there in the center like I normally would. But some of the light does get bent, and so it spreads out there off to the left and to the right. In your spectroscope, and I want you guys to actually use it today, this is sort of the demonstration of bending light, you can actually see the rainbow as it spreads out, and you don't look directly at the light in the spectroscope, you kind of look either to the left or to the right, and you should be able to see the rainbow kind of spread out from center there, okay? And that's diffraction, it's bending of waves around that little edge inside the diffraction grating there. So just to kind of show you a closer view there, that diffraction grating has tiny little holes that the light goes through, and when that happens, it bends it. So you get some of it go this way and some of it go this way, and then you kind of spread them out to see the different. You'll actually, if you look off to the left or right big enough, you'll see multiple rainbows, not just one to the left and one to the right. You'll see like another one and another one as you go there. Okay? So that's one way that light behaves like a wave. The second way that light we know is a wave, it behaves like a wave, is something called interference. Now, again, I have a video here of water waves. So in this video, this device is actually generating two waves. Right? It's just kind of bouncing up and down in the water, and it's generating two waves. You can see one being generated right here and one being generated right here. It's like just tapping in two spots. Now, this creates circles that move outward from those locations, but since it's two waves, these two waves actually interfere with each other. They influence one another. All right, when they cross, you will see, if we kind of, it's more dramatic the further you go out, When they cross, you will actually get parts where they basically destroy each other, so it's still calm water. And you'll also get parts where they actually help each other. So waves sort of have a high point and a low point. They're called peaks and troughs. So the peak, if we have two peaks that meet each other, they actually raise each other up and make a bigger wave. If you have two troughs that meet each other, they will lower each other and make an even lower wave. But if you have a peak and a trough that meet each other, they will actually cancel each other out. So interference here, you have them canceling each other out right here and then helping each other. They're adding to each other right here, making a larger wave, canceling each other out there. So you get this distinct pattern from the two waves where you have high points and then nothing, and then high points and then nothing, okay, where you can see the waves there. This is called interference. It's the combination of two or more waves interfering with each other. Now here's a video showing how light does this as well.
For this, I need a volunteer with a lot of puff. Could you come down? Your name is?
Jay.
Jay. Could you stand here? Now what you're going to do is you're going to blow through this tube, and here is sand. Now sand consists of grains, particles, lots of them, and they're all packed in here. And as Jay blows, he's actually going to blow sand through this box, up against these two slits, and the sand can pass through these two slits, very much like the two slits that we had with light. And on the back here, we've got a screen, which is going to collect the particles of sand as they go through the slits. So, huff and a puff, and blow through the tube, Jay. Keep going. Great. You can do it a little bit less. That's it. That's great. Thanks very much. Go back to your seat. I'm just going to show you what's on the screen. And this is it. It's not really a surprise. There are two stripes, very much like the two slits. Because, of course, sand consists of grains, like little particles, and they either go through one slit or they go through the other slit. And that's what you're seeing. These particles have gone through one slit, these have gone through the other slit. So this is what sand does, and this is what particles do. They produce this pattern, and it's unlike the pattern that you get with waves. Because here we have something that produces light. And the light passes through two slits, actually very close together, because light has a very short wavelength, a very small wave. So you can't actually see these two slits, but it's the same idea. And then the light passes on and hits this screen. You can actually see a pattern that's quite similar to what we saw on the tank with the water. And there are regions of bright and dark and bright and dark and bright and dark. So this set him thinking, well, if I saw the same pattern as I saw on water, and I know that waves travel on water, that must mean that light is a wave. After all, particles wouldn't do this.
So light interferes with light. If you have two light sources, they will actually combine in certain spots, and you will get this brightening here. I think this image is excellent, showing the two lights, how they combine and interfere with each other, because the light source would essentially just go straight if it weren't for this one. And everywhere where they cross perfectly, you can see they add to each other or they interfere with each other. Like these three bright light beams here, essentially, there's no source for them right in the center. It's created by these two interfering with each other and adding to each other as they move along. Okay? So diffraction and interference are two ways in which light behaves like a wave. Okay? So we can think of the different colors of light, red, orange, yellow, green, blue, violet, all the different colors as waves. And if they're waves, that means that each of these colors has different properties. Now, the way that scientists imagine light as a wave, we call it an electromagnetic wave because it is created by an electric field and a magnetic field. Essentially what happens is we have an electron that moves, and that creates an electric wave in the electric field. And that electric wave will then create a magnetic wave, because electricity will create magnetism. And so you kind of have what's called a propagating wave, where the electric wave is causing the magnetic wave. And then the magnetic wave causes the electric wave. And so they propagate each other, and so they can kind of continue on forever. Okay? However, there is a speed limit to the universe. So even though light is the fastest thing in the universe, and it basically goes as fast as possible, there is a speed limit of 3.0 times 10 to the power of 8 meters per second. All right, Einstein's theory of relativity determined that this was the fastest that anything in the universe could actually move based on the way that space-time is constructed. So light moves as fast as possible through the vacuum of space. It will actually slow down if it goes through a medium. For example, if light goes through water, it will slow down to 2.25 times 10 to the power of 8 meters per second. So there are ways to slow light down, but light is the fastest thing in the universe, and if there's nothing in its way, it will go the fastest possible that you can possibly go in the universe. By the way, this is fast enough. It's so fast, it's hard to wrap your mind around it, but it's fast enough to travel around the world 7 times in a single second. Okay? Now, when we talk about waves have two very important properties that we need to discuss. They're wavelength and frequency. Okay, so on this picture here, I'm trying to show two different waves. These two waves are different from each other in two ways, wavelength and frequency. So this wave here, we have essentially a whole bunch of waves, and they're really, really short. They're really together. We get a whole bunch of them, and then they're really, really short. So this is what we would call a short wavelength, because the length of the wave from, say, each peak to peak, or each trough to trough, is pretty short distance here. Frequency is how many of them I have at a given point. So in the amount of time that I have here from start to finish, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 waves. So the frequency of this, if this is, say, 1 second, this would be 12 waves in a second. So whatever time period this is, how many waves I have, that is the frequency. Okay, so this is a pretty high frequency, 12 waves per second. Short wavelength, though. Right, they're pretty short. This other one here, the wavelength and the frequency are completely opposite. This one has a long wavelength and has a low frequency. So the wavelength here is pretty long. There's only 2 waves here, so this would actually be 2 waves per second for the frequency. So much, much fewer waves in that second. But because there's fewer of them, each wave is a lot longer, so a longer wavelength. Wavelength and frequency are inversely proportional to each other. All right? That means that they're opposite. If one gets longer, the other gets lower. Okay? Longer wavelength, lower frequency. Shorter wavelength, higher frequency. Now, when we talk about colors, each color we found has a different wavelength and therefore a different frequency. So violet actually has the shortest wavelength. We've measured it to be about 400 nanometers. And in a second, it goes 3.00 times 10 to the power of 8 meters per second. So its frequency is in the billions. But there would be a lot more violets here because it's shorter than, say, reds. Reds has a longer wavelength, and that is 665 nanometers, so it's a bit longer. Because it's longer, in a second, travels the same distance as the violet, I would have fewer of the red waves in there, so I would have a lower frequency. All right, and everything in between. You got yellows and greens, both in between those, kind of increases as you go. The entire electromagnetic spectrum, though, includes everything that we can't see, as well as the things we can. So you've got your reds all the way to violets down here, but it's just a small portion of what's there. There's a whole bunch of stuff we can't see. Infrared, UV, X-ray, gamma ray, microwave, radio waves. Okay, now all of these are waves with wavelengths and frequencies. All right, the radio waves have the longest wavelength, so they have wavelengths that are anywhere from a meter to several kilometers. Okay, radio waves can be quite large. Microwaves are usually less than a meter. They're usually like maybe 10 or 20 centimeters, all the way down to like a centimeter. Infrared is even smaller than that, okay, but still pretty big. The visible spectrum is measured in nanometers. It goes from about 400 nanometers to like 750 nanometers. So visible light is actually a very small section of the electromagnetic spectrum. UV is even shorter wavelengths than that. Okay, so we would have to measure things in very small nanometers, or we would go all the way down into even picometers. X-rays, gamma rays, even smaller. Now, the smaller it gets, the smaller it gets in wavelength, the higher the frequency. Now, there is some math associated with this. Okay, wavelength and frequency are inversely proportional to each other. The way this is mathematically, wave speed, the speed of light, is equal to the product of wavelength and frequency. So the speed of light is equal to wavelength times frequency. So here's the equation for it. In this equation, c is the speed of light, and that is 3.00 times 10 to the power of 8 meters per second. Wavelength, the symbol for wavelength is kind of a weird, it's called a lambda, it's a Greek letter, and it kind of looks like a wave, honestly. It's basically like a little triangle with a tail up there. Kind of looks like a little cresting wave in the ocean. That is the wavelength, and it's measured in meters. Okay, the speed of light is in meters, so we want to make sure our wavelength is in meters. Frequency. Frequency is a unit called hertz. What a hertz is how many I have in a second. Okay, so a hertz is essentially per second. That's what hertz are. This many per second. It's a count per second. Okay, the symbol for frequency, for some reason it's not F, it is V. Okay, it is V. It's actually the Greek version of V, which I can't remember the name of it, but it is a V essentially. All right, so speed of light is equal to the wavelength times the frequency. Now you can use this to determine the wavelength of something if you know the frequency, or to determine the frequency if you know the wavelength. Okay? The speed of light is always going to be the same, so we don't really need to determine that. All right? So let me show you how this works. Here's a practice problem. So our equation here, c equals the wavelength times the frequency. Okay? And the speed of light, remember, is 3.00 times 10 to the power of 8 meters per second. Now it asks, what is the frequency of an electromagnetic radiation having a wavelength of 3.33 times 10 to the power of negative 8 meters? Really, really small wavelength here, but a lot of light and visible light and things like that are very small. UV, things like that. So not surprising that it's small. So we do have our wavelength, 3.33 times 10 to the power of negative 8 meters. What we don't know is our frequency. All right? So the way this works, I'm just going to take these numbers and plug them in. Okay? Speed of light is 3.00 times 10 to the power of 8 meters per second. That's equal to the wavelength, 3.33 times 10 to the power of negative 8 meters, times the frequency, which we don't know. So I'm just going to put that as an x. Okay, I don't know that one. Then I just rearrange it so that I get x by itself. To do that, I'm going to divide both sides by 3.33 times 10 to the power of negative 8 meters. That makes it go away here, so the only thing left on this side is what I don't know. So this right here, 3.0 times 10 to the power of 8 divided by 3.3 times 10 to the power of negative 8 is what I need to do. Let me grab a calculator. Now, punching this into the calculator can be tricky since it's in scientific notation. These are very, very large numbers. So one way you can do this, use parentheses around it, like I put in the equation here. 3.00 times 10 to the power of 8, parenthesis. You want those parentheses around there so it does this. It knows this is a single number. Divided by 3.33 times 10 to the power of negative 8. And I get 9.009000900 times 10 to the power of 15. So this would be 3 significant figures, because both of these have 3, so 9.0, and I'm going to round that up to a 1, times 10 to the power of 15. And this, we have meters divided by meters. What we're left with is a per second. Okay, or you could say that is a hertz, so 9.01 times 10 to the power of 15 hertz. Now, there is another way to put this in the calculator. Scientific calculators have a special button for scientific notation, and that is actually right here. It's this EE button at the second function on this calculator. Okay, so I'm going to retype this in, how you do that. So 3.00, and I'm going to hit that button, EE, and I get this little E here. That stands for this whole part, times 10 to the power of. So that takes the place of those. And then I just hit 8. Just tell it what the power is. Right? Divided by 3.33. I'm going to hit that button again, EE, to the power of negative 8. And I get the exact same answer. This one is less buttons to push because I don't have to use the parentheses, because it understands if I'm using that button, these go together as one number. Right? So 2 ways to enter this. Okay, your turn. So what is the wavelength of electromagnetic radiation that has a frequency of 2.25 times 10 to the power of 11 hertz? Remember, the frequency is how many I have in a second, so these wavelengths, we're going to have a lot of them, so that's a very high number there. So the frequency here, you're going to solve this the same way. But now instead of finding wavelength, you are finding instead of finding frequency, you are finding wavelength, and you have the frequency. Okay, so pause the video and see if you can come up with an answer. Okay, so we have our equation. C equals this wavelength times the frequency. Here is my frequency right here. The speed of light is 3.00 times 10 to the power of 8 meters per second. So that's what the speed of light is. Okay? So I'm going to take in the 2 pieces of information I know. The one thing I don't know is the wavelength. I'm going to plug them in here. So 3.00 times 10 to the power of 8 meters per second is equal to the wavelength I don't know, so x, times the frequency, 2.25 times 10 to the power of 11 per second. Okay, isolate x by dividing both sides by 2.25 times 10 to the power of 11 here. Gets rid of this. So, punch this into the calculator. .00 second e to the power of 8 divided by 2.25 second e to the power of 11. And I get a pretty small number here. 0.0013333333. Each of these has 3 significant figures, so I'm going to round that to 0.00133. 0.00133. For units, the per second cancels, so what's I'm left with is meters. So the wavelength is 0.0133 meters. Now, what type of electromagnetic radiation is this? Well, if I take a look here, this is times powers of the 10. So this is essentially 1 times 10 to the power of negative 3. So it would be about right here. So microwave. This would be about a microwave for electromagnetic radiation.